Buongiorno! Today we will be talking about the gradient of a function, which is something that we touched upon on the previous video about directional derivatives. In that video, we used the gradient only as a kind of notational shorthand. We didn't actually ascribe any particular meaning to it. That will be rectified today, where we will discover that the gradient of a function tells us quite a lot about that function. The functions that have gradients are of this form. They are real-valued functions of several variables. Such functions, by the way, are sometimes called scalar fields. It's a funny sort of name, but it actually makes some sense. The idea is that if I have such a function, like a function from R2 to R, at every point in the domain, the function associates a scalar with it. Like maybe at this point, the value of the function is 9, and at this point, the value of the function is 18, and at this point, the value of the function is minus 22. The terminology scalar field is supposed to make us think about that association of points with scalars. So at every point, you can imagine a scalar somehow attached to it. I used the example of temperatures in earlier videos, where I said the temperature here is 14 degrees, and the temperature here is 58 degrees, and whatever. The important point being that at every point, I was attaching a scalar. So you could almost think about this as being like a whole literal field of numbers. At every point, you have some kind of a scalar attached to it. And of course, the same thing is true if we had a function from R3 to R. That would be another scalar field, because at every point, we would just have some number attached to it, some scalar. Maybe here the value is 63, so I can think of a scalar being attached to that point. And here the value is 107, so I can think of a scalar attached to that point. And maybe here the value is 0, so I can think of a scalar attached to that point. This function g is another scalar field. It just takes points and turns them into scalars, or associates scalars with each point in the domain. And this is true even if we were looking at a function from R42 to R. It's a real-valued function of several variables. We could also call it a scalar field, because whatever 42-dimensional space looks like, each point in it has 42 coordinates, and what this function h does is you stick in those 42 coordinates and it gives you back a scalar. So you can think of this as a scalar field, because what h is doing is just attaching scalars to every point in 42-dimensional space. Okay, that's enough terminology. Let me remind you of how we defined the gradient of a scalar field. If we have a scalar field, such as this one, then the gradient of this function is a vector, namely the vector that consists of all of the partial derivatives of this function in the conventional order. So if f is defined this way, then the gradient of f, where this is our symbol for the gradient, is going to be this vector, since this is the partial of f with respect to x, and this is the partial of f with respect to y. And I've written here the gradient as a function of x and y, because that's what it is. It's a vector, but its components depend on the particular values of x and y we place into the function. For example, if we put 0, 0 into the gradient of f, we get the vector 0, 0. We get the 0 vector. Whereas the gradient of f at 1, 1, well, if we put 1, 1 in there, we get the vector 2, 4. And the gradient of f at minus 2, 1, well, if we put minus 2 and 1 in there for x and y, we get the vector minus 4, 4. Okay, you get the point, but something interesting is happening here. The gradient, viewed as a function, takes points in Rn, R2 in this case, and turns them into, not real numbers, but turns them into vectors in Rn, R2 in this case. So the gradient is sometimes referred to not as a scalar field, but as a vector field. Because rather than taking points in R2 and associating numbers with them, associating scalars with them, like taking this point and saying, well, that's got the value 5 there, and this has the value 14 there. What a vector field does in R2 is it takes points from R2 and associates a vector with each point. So instead of putting a number at each point, it's essentially putting a vector at each point. So like in this example, at 0, 0, it's putting the 0 vector there, so I'll just put a dot there. Whereas at 1, 1, it's putting the vector 2, 4 there. So if we go to the point 1, 1 right here, what the vector field is doing is putting this vector 2, 4 right there, like this. Meanwhile, at minus 2, 1, which is this point right here, what the gradient is doing is laying this vector minus 4, 4 down, which looks something like this. And you could imagine that at every single point in R2, we've got some vector associated with it, which is the gradient of f at that point. So now you have this whole plane filled with vectors pointing in different directions. Vector fields are used extensively in physics to model force fields, whether electromagnetic fields, gravitational fields, or what have you. And if we're lucky, at the end of this quarter, we'll have time to talk about vector fields in greater depth. For now, I'll just mention that with the appropriate software, you can draw a picture of a vector field, and I have plotted this particular vector field using Wolfram Alpha, and the result looks like this. Now, when you plot a vector field with computer software, it actually rescales the vectors within the field so that they all actually show up and you can tell what's going on. If we drew all of these vectors at their actual size, which was what we were trying to do over here, it would just look totally chaotic. The point of such a vector plot is just to give a global feel for what the vector field looks like. Here, when x is 0 and y is 0, we get the 0 vector, and when we're close to the origin, we have a small force, if you want to think about it that way, pushing us away. We have very small vectors, and the further away we go from the origin, the larger those vectors get. The more complicated the vector field is that you're plotting, like here's this one, is very, very simple, the more complicated a picture you will get down here. And though sometimes with even very simple ones, you can get pretty interesting pictures. But as I say, that's not really the topic we want to discuss today, except in as much as I want to remind you that the gradient of a scalar field like this actually is a vector field. So you could think of, you start with a scalar field, you take the gradient, you end up with something like this, which really does correspond to a vector field. Not every vector field, by the way, is the gradient of a scalar field, but those vector fields that are gradients of scalar fields have special properties, which, as I say, we may get to at the very end of the quarter. I just mention it here as something to look forward to. What I really want to talk about today are some basic properties of the gradient and interpretations of the gradient. Most of what we will talk about follows from a result that we saw in the previous video about directional derivatives, namely the formula we derived for computing directional derivatives, that the directional derivative of what we would now call a scalar field at a particular point can be computed by taking the gradient of the scalar field at that point. So that's going to be a particular vector, and dotting it with the unit vector in the direction in which we want to take the derivative. The last video was devoted to deriving this formula, doing a few examples of actually computing directional derivatives, and ensuring that you have a good interpretation for what this thing actually means. Today, I want to look at this formula again and really dwell on the role of this gradient, not just as a notational shorthand, but as an important thing in its own right. This formula tells us something about this gradient. To see what I mean, let's start by supposing that our scalar field, whose derivative we were taking, is a function of 3 variables. In that case, I can't draw the graph of the function because it would require 4 spatial dimensions, but I can at least draw the domain. So the domain of our function f lives in R3. Let's just say it's all of R3. Then, since f is a scalar field, for every point in R3, this function f associates a scalar to it, which is this w. So you can imagine at every point, there's some value, some temperature. Now let's say we have some point in the domain, and we might want to take the directional derivative of our function of 3 variables in any of infinitely many possible directions. And this formula tells us how to do it. Okay, we know that much already, but whichever direction we pick, whether it's this way or 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 whatever, we end up computing it by taking this dot product. And again, no matter which direction we're taking the directional derivative in, one of the 2 factors in our dot product is going to be this gradient. That is fixed. The gradient of the function at p is some fixed vector. That doesn't change. U changes depending on which direction we're taking the derivative in, but this gradient is always the same because the gradient of f is just that vector made up of the partials, and we evaluate it at the coordinates of that point, which don't change. So this gradient of f at p is some definite vector. Let's say this one. Now, when we take this directional derivative, we could take it in any of infinitely many directions, and we're going to specify the direction by a unit vector. For the sake of argument, let's just say this is the unit vector we are talking about. So we want to take the directional derivative in this direction. We're thinking about how the scalar field f changes as we move from p in this direction. Now we know how to compute that directional derivative. That's not the problem. What I'm after here is a way of interpreting it that will throw some light on the gradient, on this particular vector right here. So let's think about this dot product. The directional derivative is going to be the gradient dotted with this unit vector. Now we have to go back to what the dot product actually means, how we defined the dot product in the first place, not how we compute it with coordinates, but what it actually means. Hopefully you remember, or if not, you can review, that this dot product is a product of two specific numbers, namely the length of one of these vectors multiplied by the scalar projection of the other back onto the first. And we can do it in either way because we know that the dot product is commutative. So let's say that this dot product is equal to this, the scalar projection of the unit vector onto the gradient, which in our case would look something like that. It's the shadow cast by the unit vector down onto the gradient, multiplied by the length of the gradient itself. Well, now let's think about how this directional derivative, how its value changes if we move in different directions. It's always computed the same way, and this is always going to be equal to this. Of these two factors, one of them stays the same, no matter which direction we're taking the directional derivative in. Namely this one. That doesn't change. That's just the length of that blue vector. The only thing that changes is this scalar projection of the unit vector onto the gradient. That will vary with the direction of the unit vector. I think this will be easiest to understand if I redraw this picture in a larger form, like this. I've got my point P, and let's say that this vector right here is the gradient of f at P. Now if I'm taking a directional derivative of f at P, I can go in any direction, but the direction I go in is going to be specified by a unit vector. So that means the tip of my unit vector will of course be lying on a sphere of radius 1 centered at P. So let me go ahead and draw that sphere in. Okay, there it is. So when I'm taking my directional derivative in the direction of some unit vector, the tip of that vector will have to lie somewhere on the surface of that sphere. And wherever it lies, say right there, if we compute the scalar projection of that vector onto the gradient and then multiply that scalar projection by the gradient, we get the directional derivative in that direction. This already gives us a nice feel for how the gradient contains all of the directional derivative information in and of itself. But let's make a few simple observations. I've drawn this sphere so that the equator is right here and that the gradient is cutting through at the North Pole, as it were. If I take the directional derivative of f in any direction and the unit vector is pointing at a point in the northern hemisphere, then no matter where it lies, maybe it's something like that, that scalar projection is going to be positive, and so I'll have a positive times a positive, which means that the directional derivative in that direction will be positive. So if I'm moving in any direction going through the northern hemisphere, then my directional derivative will be a positive number. I have a positive rate of change through this northern hemisphere. Meanwhile, if I want to take the directional derivative in a direction through this southern hemisphere at any point, like let's just say in this particular direction, where my unit vector makes an obtuse angle with the gradient, then what can I say about the directional derivative in that direction? Well, definitely it's going to be negative, because the scalar projection of this unit vector onto the gradient, remember how that works, I have to project it backwards onto the extension like that, and then I pick up a negative sign. So I get negative whatever that length is for my scalar projection. So if I were to take the directional derivative in this direction, I'd get minus whatever that length is times that. So I would get a negative directional derivative. And this would be the case in any direction whatsoever, as long as my direction is pointing into that southern hemisphere. In other words, as long as my direction vector is making an obtuse angle with the gradient vector. Interesting. Now, what if I had a unit vector? What if I'm taking the directional derivative in a direction that actually lies along the equator, like this, if I'm moving in this direction? Well, in that case, then my unit vector is at a right angle to my gradient vector, which means that its scalar projection onto the gradient vector is 0. And then the product of these two numbers would be 0, which means the directional derivative in that direction would be 0, as it would be in, say, that direction, or this direction, or this direction, any direction that actually is at right angles to the gradient. So once I have my gradient, I can think about this little sphere around it, and I've got the northern hemisphere, where we have acute angles with the gradient, and I will therefore have a positive directional derivative. I will have the southern hemisphere, where I'll have a negative directional derivative because of that obtuse angle with the gradient. Then any direction in which my unit vector points to somewhere on the equator, where I have a right angle with the gradient, I have a directional derivative of 0. That's quite tidy. That is not the kind of thing you probably thought of immediately when you saw this in the last lecture, but it is so. But there's more to say. Let's just concentrate our attention on the northern hemisphere right here. We'll just go in directions that give us a positive directional derivative. So directions where the function f is increasing. Let's just concentrate on these two directions right here. Let's say I've got my scalar field f, and I want to think about taking its directional derivative in this direction, and also its directional derivative in this direction. We know that they're both going to be positive, that the function is increasing in both directions. But can we say, without knowing anything specific about the function f itself, can we say in which direction the function will be increasing faster? We can. And I think you will see right away that it's going to be in this direction the function is going to be increasing faster, because if we take the scalar projection of this vector onto the gradient, I get something fairly large, whereas if I take the scalar projection of this vector onto the gradient, I get something relatively smaller, which means that, and since we're multiplying them both by this same thing, this one will give us a bigger product, hence in this direction the derivative will be greater. So if I wanted to maximize the directional derivative, if I said, here I am at point P, and maybe once again we'll think of F as representing temperature, and I want to get warm as fast as I can, what's the direction in which I will heat up most quickly? I know I'll heat up in this direction, and I know I will heat up in this direction, and this direction, and this direction, anywhere in this northern hemisphere, but what direction will heat me up the quickest? Well, that will be the direction that maximizes the scalar projection of the direction vector onto the gradient. Well, you can see what direction that's going to be. The closer I get to the North Pole, the bigger that scalar projection will be. It will be maximized when I'm actually at the North Pole. That is, if I'm at this point P and I want to increase my temperature or increase the value of F as rapidly as possible, the direction I want to move in is in the direction of the gradient itself. So the gradient points me to the direction in which the function f increases most rapidly. This is a very important fact, important enough that I'm going to put it in its own little box once I move some of this stuff around a bit. So what we've seen is that a consequence of this directional derivative formula is that the gradient of f at P is a vector that points in the direction from P in which f, the scalar field, increases its value most rapidly. That's a nice qualitative result, but we can say something quantitative as well. So we know that if we are at P and we want to increase the value of f most rapidly, we should move in the direction of the gradient. But if we do move in the direction of the gradient, how fast is that maximum rate of change of f? Well, that's very easy to see, once again, just by looking at this formula. I'll add the result over here. Moreover, f's rate of change in this direction, in the direction of the gradient, which will give us the maximum rate of change. So f's maximum rate of change at P is, well, let's think our way through it. It's going to be the scalar projection of u onto the gradient. Well, u is going to be pointed along the gradient, so it's going to be the length of u will be its scalar projection. But the length of u is 1, so this would just be 1 multiplied by the length of the gradient. So we have 1 times the length of the gradient, so it's going to be the length of the gradient itself. So the maximum rate of change of f from this point, which is going to be in the direction of the gradient, will just be the length of the gradient. So the rate of change in this direction is the gradient's length. This is important enough to be boxed up in royal purple. We've already come a long way from the last lecture on the directional derivative, where we just use the gradient as mere notation. But we now see that the gradient has real geometric meaning in and of itself, both its direction and its length. Its direction gives us the direction of most rapid increase of the function, and its length gives us the actual rate of increase in that direction. And while I developed this picture in 3 dimensions because I somehow like it, the idea of this northern hemisphere and southern hemisphere and so on and so forth, the analog works in any number of dimensions. Usually we would be seeing it in 3 or 2, and it's the exact same thing in 2 dimensions. If we have any point in our domain of f, and we have the gradient of f at that point, then all the unit vectors will lie on a circle instead of a sphere. And if we move in any direction that makes a acute angle with the gradient, we will have a positive rate of change, a positive directional derivative. Down here we would get a negative directional derivative because the scalar projection would be negative in that case. And if we move at right angles to the gradient, we will have a directional derivative of 0. And above all, the gradient itself points in the direction in which the scalar field is increasing its value most rapidly from p, and its length gives us the actual rate of change. But the direction is often the most crucial thing right there. We want to know how to move as fast as possible from that point. It's going to be in the direction of the gradient. And maybe I should bring up one more bit of computer graphics to give you a sense of how this thing helps us think about the meaning of the gradient. To see what I'm talking about, let's consider this function right here. This is a real-valued function of 2 variables. It's a scalar field. We could discuss what the graph of this thing looks like in 3 dimensions, which we could do by doing the usual business about thinking about slices of the graph, looking at cross-sections, but we don't need to do that right here. I just want to think about what happens as we move around in the domain in 2 dimensions. Given any point in R2, we pop its coordinates in there, and we get some scalar associated with it. For example, at this point right here, whose coordinates are 2, 1, if we pop those coordinates in, we get 4 minus 2, which is 2. So I'll just put a little 2 here to remind us of the value of the function at that point. Meanwhile, at the point 1, 3, the value of the function would be 1 minus, minus 18. So that would be minus 17. So I'll label that point with minus 17. Again, if we want to think about these as temperatures, it's minus 17 here, it's 2 degrees right here. And you can imagine that at every point in the plane, there is a scalar associated with it. So we have this scalar field here represented quite literally by putting a scalar next to every point. And now if we're standing at any point on this plane, like let's say this one right here, which is at 1, 3, where the value of the function is minus 17, suppose I want to move in a direction so as to increase the value there. Well, I can see lots of directions seem to do the trick, but which direction should I go in if I want my rate of increase to be as rapid as possible, at least within an infinitesimal neighborhood of that point? I may have to change my mind once I've gone a little way and reassess. Well, we now know that the direction we want would be the direction in which the gradient of f is pointing at the point in question. And the gradient is easily computed. Here, for example, the gradient at 1, 3 is this vector 2 minus 12. Now on the scale I have it drawn here, 2 minus 12 would be this huge vector. I don't want to actually draw that thing in. If all I'm interested in is the direction in which I want to travel, I could just draw a vector in that is in the direction of 2 minus 12, but scaled down somewhat. And if I did that, maybe it would ultimately look something like this. And if I imagine doing that at all of my points here, and many others besides, I would get the actual vector field. That would be a horrible thing to try to draw by hand. So I've brought up a computer picture for you, and here it is. This is the plot of this vector field, the so-called gradient field of this scalar field. And we could even pick out, if we went to, let's see, positive 1, 3 is going to be somewhere around here. So maybe that vector right there, which is very small, but you can see it's pointing in the general direction as the one I have right there. Now what this gradient field, what this picture does for us, when we think about it in terms of our new interpretation of the gradient as giving us the direction of most rapid increase, it gives us a sense of what direction you would have to go to if you were dropped anywhere in this field if you wanted to move in the direction that maximized the value of the function as rapidly as possible. So if you happen to be dropped down somewhere down here, well, in general, you're going to be going in this direction roughly, kind of a northwesterly direction, until you reach a certain level here where you're going to want to suddenly start going west. And it looks like you've got kind of an asymptote here at the x-axis. And you can see why this is if you think about the function here. You're trying to optimize this. You're trying to make this thing as large as possible. Well, in general, the way to make this as large as possible, you want the x-coordinate to be large. Making the absolute value of that x-coordinate large will enlarge f's value. And you want the y-coordinate, the magnitude of the y-coordinate, to be small, because the larger y is, the more you have to subtract off the value, and you don't want to subtract anything off. You want f's value to be as big as possible. So no matter where you're dropped in this thing, say right here, you want to bring that y down. So you want to get down towards the x-axis, but you want x to be made large. So you also want to push in the other direction. And the precise angles at which you want to push and pull, well, that's all given by this gradient right here. If you've studied a little differential equations, you may have seen things like this before, because if we think of the actual curves that are traced through here that are tangent to the various vectors we have, those would be the solutions to a certain set of differential equations. But that is for another day, the day that won't occur in this class, unfortunately. But take it as an advertisement to study differential equations, which is a nice subject. There is another important property of the gradient that we need to talk about. But before we can do that, I have to introduce the idea of level sets, which include such things as level curves, level surfaces, and higher dimensional analogs too. So what are they? Well, the first thing I should note is that we talk about level sets of scalar fields. Any scalar field we might be given, any real valued function of 2 variables or 3 variables or 4 variables or whatever, has level sets. So these are something that are defined only for scalar fields. Anyway, the idea is that if I have some scalar field, let's say it's a function of 2 variables, if I were to set this equal to some constant, like so, the set of points that satisfy this would be called a level set for the function f. Take, for example, this function, an old friend of ours. We know what the graph of this thing looks like in 3 dimensions. It's a elliptic paraboloid. Some level sets for this function might look like this. X squared plus y squared is 0, or x squared plus y squared is 1, or x squared plus y squared is 2, or x squared plus y squared is 63. And if we were to plot those level sets in the xy plane, we might get something like this, where the bullseye here corresponds to the case where c was equal to 0, and this next ring corresponds to the case where c equals 1, and of course this circle would be the case where c is equal to 2. And given this particular function that we were working with, all of the level sets, of course, will be circles, at least when this constant is positive, and when it's not positive you don't get anything, or at best you get 1 point like that. You can think of this family of level curves as a kind of topographic map of the graph of the surface, of the graph of f. Here is the familiar paraboloid shape, and when we took these level sets here, these level curves, what we were doing was we were holding the output constant. So for example, when we were looking at x squared plus y squared is 1, that particular level set, okay, we know that's the unit circle, but we could think about that in this 3-dimensional setting as corresponding to, we're holding the output, which goes with the z variable, we're holding that output constant at 1. So it would be like we were taking our surface and intersecting it with the plane z equals 1, like so. And when we do that, of course, the intersection will be a circle. And this level set right here, where we set the z variable equal to 2, would be the intersection of this surface with the plane z equals 2, the result being another circle of intersection, which corresponds to that circle right there, and so on and so forth. That brings us to the interpretation of this as a topographic map. You've probably seen things like this if you've spent some time hiking and you look at maps of mountains and you want to figure out which trails are particularly steep. The labels I have here, like c equals 1, c equals 2, c equals 4, you could think of those as corresponding not just to the heights here, but to altitudes in general. Even if we didn't know what this picture looked like right here, just seeing this one right here, we would see that, okay, down here, where c equals 0, if we interpret that at the height, I'm at the bottom of a valley. And no matter what direction I walk up, I'm going to get to something here that's a quarter of whatever unit high. And then the altitude reaches 1, and then it reaches 2, and then 4, and then 5. In any direction I go, if I'm on this circle, that is the set of all points where c is 2. Just like on an actual topographical map, you might see some kind of something like this, corresponding to a hill, and maybe this is 100 feet high, and 200 feet high, and 300 feet high, and maybe there's a little peak right there where it's around 400 feet high. And from a map like this, you have a sense that going from, say, here to here is a very rapid ascent of 100 feet, whereas you could make that same ascent from here to here over a much longer period. Which of these two paths you take probably depends on how strenuous you want your exercise to be. Anyway, the level sets of a function of two variables like this one are, as we have seen, level curves. In fact, they're curves in the plane. Now, if we had a function of three variables, such as this one, x squared plus y squared plus z squared, now I can no longer see the graph of this function because I would require four variables, 3 for the inputs and 1 for the output, but I can still talk about the level sets of this function. Instead of level curves, they would now be level surfaces because the level sets would be of this form. F of x, y, and z is equal to some constant c, such as these. And each of these equations, each of these level sets, is in fact the surface of a sphere. Here are two of them, for instance. And remember, this bit of R3 here, this is just the domain of F. We can imagine a point moving around in here, and at every place the point is, the coordinates of that point popped into the formula for F would give us some value. There's some scalar associated with that point. Maybe it's 21, who knows? It's definitely positive because we get the sum of three non-negative numbers right there. And if from that point we moved around on some curve in R3, then at every position on that curve, the value of the scalar field would be different. Maybe over here it turns out to be 47. At every point in this domain, the scalar field has some particular value. What's special about the level sets is that the value remains the same throughout. So if I'm looking at this particular sphere right here, where c is equal to 2, that means that if I took a point like I had right here, and I asked, well, what's the value of the scalar field right there? Well, I know what it is. It's 2. And if we let this point wander all over this sphere, never leaving its surface, and I take some other point on that curve, I don't have to ask, gee, I wonder what the value of the function f is at that point. I know what it is. If it's on that level surface, it's going to be 2. That is precisely what defines that level surface. That is the set of all points in R3 that get mapped to 2 by this function f. It's like the example of the topographical map I gave a moment ago. If you are standing on one of these curves, it tells you that your altitude is 100 feet. You could walk all over that curve. So long as you stay on that curve, your altitude doesn't change. It's 100 feet. Something similar is happening on this level surface, on this sphere. You could wander all over this sphere, and your altitude, you'll have to supply the air quotes right there, your altitude in some fourth dimension remains the same. It's going to be 2 units. But we don't have to think about what's happening in a fourth dimension. We just have to remember that the value of the function f remains constant whenever we are on the surface of that sphere. By the way, if I have a function of 4 variables, like this, now I can't even show you the domain because the domain lives in 4-dimensional space, and the graph of this function would live in 5-dimensional space. I can still talk about the level sets of this function, I just can't picture them anymore. The level sets would be when this stuff is equal to any particular constant. Each level set would be an equation involving x, y, z, w, and then this would all be equal to a constant. So x, y, z, and w would be the 4 variables, meaning that the level set would live in 4-dimensional space. Again, we don't need to be able to see it to be able to talk about it. The idea being that if I set this equal to some constant, to 912, there is some geometric object, some hypersurface in four-dimensional space, consisting of all the points x, y, z, w that satisfy this equation. That would be a level set for the function I had written down a moment ago. Okay, I think you understand what we mean by level sets. All of this is just a prelude to another property of the gradient about its relationship to level sets. So, suppose I have a function of two variables, and I'm looking at some level set of that function. So that could be some curve like this in R2. And suppose I have a point that lies on that level set. The question I want to pose is, what does the gradient of f look like at P, at any point on the level set? If we think this through, we'll find the answer pretty quickly. It may help to back up and just set the scene a little bit, just to remind you of what's going on, because there are a lot of concepts in play here. First of all, we have this function of two variables. It's a real valued function of two variables that is a scalar field. That means that everywhere in R2, everywhere in the domain of f, at every point there's some particular value. Here, for example, are a sprinkling of points, and to each point there is some scalar attached to it, the value of those points at the function. I've just made these numbers up, of course. And that is true of every point in the domain of f. F is a scalar field. Now, as we discussed earlier, every scalar field has a gradient associated with it, a gradient field. Now, the gradient field is a vector field. That means at every one of these points, there is some vector sticking out, right? The gradient of f at that point, and that vector, that gradient, tells us the direction we have to move in for the most rapid increase of the value of the function in an infinitesimal neighborhood of that point. So to return to my question, if I take a point on a level set, on a level curve of this function, what will the gradient look like there? Well, you might be asking, what does the fact that this is a level curve have anything to do with it? Remember what is meant by a level curve. At every point on this curve, the value of the function f is the same thing. It's whatever this constant is. So if I go for a walk on this curve and follow the value of the function, like these numbers out here, whatever it is there, see, it stays the exact same. It's very boring. The value of the function wouldn't change at all. So if I want the gradient, which is going to give me the direction in which this thing changes most rapidly, the last thing I want to do is walk along the curve itself, because there the value of the function doesn't change at all. In fact, since the value of the function doesn't change at all on the curve, the gradient is going to point in a direction that gets me away from the curve as fast as possible, because the curve represents stasis, and we want dramatic change. Well, locally, on an infinitesimal scale, the curve is indistinguishable from its tangent line. If you were an infinitesimal-sized bug walking around from point P on the tangent line, you wouldn't be able to tell the difference between that and the curve, and it would appear that the value of the function was constant on that tangent line, again, in an infinitesimal neighborhood. Well, if I want to get away from this situation of stasis and see the function change as rapidly as possible, I need to move at right angles to that thing. That tells me where the gradient is pointing. It's going to be at right angles to the curve. It's going to be normal to the curve, like this. And that is going to hold everywhere on the curve, because this curve is a level curve. If I take some other point on the level curve, what does the gradient of f look like there? It will be perpendicular to it. What will the gradient look like at that point on the level curve? It will be perpendicular to it. And that will be the case at every point on this level set. And it is crucial that we are talking about a level curve. The whole reason, remember, the whole reason these gradients are perpendicular to the curve is that on the curve, the value of the function is not changing, and the gradient points in the direction of greatest change. So get away from that situation of stasis as fast as possible. I should point out that all of these vectors could be facing the opposite way. They could be facing inside. That will depend upon the nature of the particular function. Essentially, the difference is whether I'm in a valley climbing out by following the gradient, or we could have another situation where I'm trying to get to the top of a hill, in which case these would all be facing inwards. Anyway, this property is sufficiently important that it too merits being boxed up on the side here. I'll call it a consequence squared, since this is a consequence of what we proved earlier about the gradient pointing in the direction of most rapid increase, which in turn was a consequence of this formula for the directional derivative. So try to remember not only the results, but the logical flow of these ideas. It will help it all stick in your mind much, much better. Anyway, the gradient of f is perpendicular to f's level sets. And of course, this statement only makes sense if f itself is a scalar field, a real-valued function of several variables, because only such functions have gradients, and only such functions have level sets. And of course, there was nothing special about functions of two variables. If I have a function of three variables, and I look at a level set of that function, which would of course be an object in three-dimensional space, like this blob, this would be the set of all points in three-dimensional space that get mapped to c, some constant, by f. It's the same story here. Remember, at every point in three-dimensional space, this function sends those points to particular values, particular scalars, maybe something like this. At any rate, every point on this surface gets mapped to the same place, namely to whatever constant this is. So if this is going to go to C, this is going to go to C, this is going to go to C. If I have some other point on there, that's going to go to C. It's pretty boring. We could walk around on this surface all day long, and because it is a level surface, the value of the function, the temperature, if you want to think about it that way, would never change. So if we're at some point on this surface and we want to know what's the gradient of this function here, well, the gradient of the function here might look like that, or here it might look like that, or here it might look like that. Who knows? But here I do know what the gradient's going to look like. I know it is going to be at right angles to this level set, meaning at right angles to the tangent plane of the level set at every point. And this will be true everywhere on the level set. Again, I have no idea what the gradient might look like here or here or here, but everywhere on the level set, the gradient will be perpendicular to the set itself. This might seem to be just an interesting curiosity. It's more than that. This fact has a lot of applications. I'll show you a quick one right away. This fact gives us a way of computing tangent planes to many surfaces, not just the graphs of functions of two variables. Here's our problem. Find the equation of the tangent plane to the surface given by this equation at a particular point. We can verify that this point does, in fact, satisfy that equation, but what does the graph of this thing look like? That is not an easy thing to figure out. But as it turns out, it doesn't matter. I can solve this problem without actually knowing precisely what the graph looks like. The trick is to look at this from the right angle. That surface can be viewed as a level set, namely as the level set of this function, xy squared x cubed. This would just be f of x, y, and z is equal to 12. So I don't particularly care what this looks like. I'll just draw a quick schematic blob here to represent it. This isn't supposed to be remotely accurate. It's just to help us in our thinking. Now we have a point on this level set. It happens to be 3 minus 2, 1. Well, we're looking for a tangent plane. Now a tangent plane is just a plane. What information do we need to write down the equation of a plane? Well, we need two things we know. We need to know a point on the plane, which we already do because we're looking for something like this. And we need to know a normal vector to the plane. Aha! Now I have a very, very easy way to come up with that normal vector, because I know that the gradient of f at this point will be normal to the surface, and therefore normal to its tangent plane. Let me write this down. Thus, the gradient of f at 3 minus 2, 1 will be perpendicular to the surface, and hence to the required tangent plane. All that's left now is to compute this thing and then write down the equation of the plane. As you can confirm on your own, the gradient of this function is this expression right here. When we pop these coordinates into that expression, we end up with 4 minus 12, 36. So the gradient would look something like that. But these numbers are larger than I like, so I can just scale this down. I'll divide everything by 4, and I will still get something, even after I've scaled this back, that will be normal to the plane I want. Thus, this vector 1 minus 3, 9 is perpendicular to the required plane. So I've got a normal to the plane, and I've got a point on the plane. Putting those two pieces of information together, we can conclude that the tangent plane's equation is this, by the equation for a plane that we developed quite some time ago now. Or equivalently, if we massage this a little bit to put it in a nicer form, we end up with this. And we have our tangent plane. Hooray! Notice that we could have actually solved this problem by taking this equation, explicitly solving for z, in other words, making this z is equal to the cube root of 12 over xy squared, and then started taking partial derivatives. It would have been horrible, especially with that cube root in there. This avoids all that, and it has a nice, elegant flow to it as well. And there are other cases, of course, where I could have an equation of 3 variables in which I cannot disentangle them and can't solve for z. And in that case, I can still use this technique to come up with the equation of the tangent plane. Okay, you have now met the basic properties of the gradient. You will see them again. Until next time, ciao.